Swayam Prabha. Digital India. Educated India.
Hello everyone, and welcome back. We are going to talk about geologic considerations in tunneling in today's lesson, but as is the practice, we are going to look at the solutions of the previous question set. This is the question set that I gave you as part of the previous lesson. The first question was: a closely spaced family of thrust faults runs parallel to the Himalayas. What is the direction of the major principal stress along the thrust faults? Now let's say the if you look at the northern part of the country, then it might actually look like this, and the Himalayas run in this direction. So basically what we are having here is that there are a bunch of thrust faults that run near the foothills of the Himalayas. So basically if you look at the section here, then the thrusting is going to be like this. So this is section AA. So basically what is happening is this is one block in this case, and another block to the further north is like that. So this is the northerly this is the direction to the north, and this block basically is squeezing against the block that is to the north. So in this case, obviously the direction of the major principal stress is in this is towards the north. So that is what I asked in the first question. Now let's look at the second one. Would you expect a sample of gneiss to be stronger in the direction parallel or perpendicular to the bedding? Now let's consider this question once again. So let's say that the gneissic rock has got bedding planes oriented in this manner. So obviously the depositional environment was such that the major or the environment under which this particular rock was formed was such that the major principal stress was in this direction, and as I have indicated in the previous lesson, the grain contacts are going to predominantly develop, or more contacts are going to develop in the direction of the major principal stress. So it is going to behave in a much stronger manner in the direction of the major principal stress. So that gives the answer. This particular specimen of rock is thus going to behave in a much stronger manner if you consider the strength perpendicular to the bedding direction as opposed to the direction parallel to the bedding planes. The third question was: explain why folding becomes more prevalent with depth compared to faulting, and this is something to do with the brittleness of the stress strain behavior of rock, and what we have seen from previous lessons is that a rock is going to behave in a brittle manner provided the confining pressure is low that means the rock is at a shallow depth below the surface of the earth. Then the second important aspect is that the temperature should also be low, and the third aspect here to consider is application of stress is relatively rapid. So, all these things, all these aspects are going to lead to a brittle behavior of the rock mass. So, you look at the first 2 points, first 2 bullets here, and it will be obvious that if a rock specimen is near the surface of the earth, it is going to behave in a brittle manner because the confining pressure is low and also the temperature is low near the surface, and temperature in fact starts mounting up as the depth increases. For instance, if you go down to a depth of a kilometer or so, then the temperature over there is going to be about 30 degrees more than the 30 degrees Celsius more than the temperature at the surface of the earth. As a result of which, if the same type of rock is occurring at a great depth, a few kilometers below the surface of the earth, then it is going to behave in a much more ductile manner compared to the specimen which is near the surface. So, all these reasons are pointing towards the fact that we are going to get a brittle behavior when we have got we are considering an element near the surface, and because of the fact that brittle behavior leads to faulting and ductile behavior on the other hand leads to folding rather than faulting, we get more faulting near the surface of the earth, and the amount of faulting becomes less and less prevalent as the depth becomes more and more. So, those are the 3 answers to the questions of the previous lesson. Now, we move on to today's lesson. What we want to accomplish at the end of today's lesson are as follows. We would like to be able to list the major geological considerations in tunnel construction, and we should be able to list the typical measures to account for various types of instability because of the rock mass behavior and because of groundwater during the construction of tunnel and operation of tunnel. Okay. So, first of all, what comes to mind is what is a preferred geological setting to construct a tunnel, and if you try to just look at the problem logically, then it would appear that if you have got a very strong mass of rock which is relatively free from joints or other structural features like shear zones or faults or other fractures, it is relatively free from bedding or lamination, then that is going to give us a very ideal situation to construct a tunnel. Now, if you construct a tunnel in that kind of geological setting, then such tunnels are going to be often self-supporting. The tunnel can be constructed by either blasting or boring, but here you have to account for a certain type of problem and that is associated with stress concentration, because in this case the rock mass is relatively strong. So it is going to attract quite a large concentration of stress, particularly near the corners of an underground excavation, and such concentration of stress could in fact become so large that under that amount of stress the rock mass is going to fail in an often explosive manner, because strong rocks are often brittle, so they are going to fail in an explosive manner, and what it going to end up in is a phenomenon called rock burst. Okay. So that gives us a preferred geological setting, but a preferred geological setting is not often the case, and what we are left with is a much worse situation than the ideal conditions that we just now discussed. So let us say you have to construct a tunnel through soft or jointed rocks. The condition here is typical of a terrain of clay stones, shales, brittle or poorly compacted sandstone. It is just like cemented sand. In fact, it is very soft. So if you take a small piece of friable or poorly compacted sandstone, then if you under pressure of your finger pressure, the sandstone is going to crumble. It is so soft. Then chalk is another of those soft or jointed rock species. Limestone, dolomite, phyllite, slate, and rock mass, all types of rock species that are crisscrossed with relatively closely spaced joints, folds and faults are in this category. Now, if you have got a rock of this type, then the tunnels that are going to be constructed, the tunnel walls in fact are not going to be self supporting. So more often than not, you are going to be set with a problem of designing some measures in order to stabilize the possible failure mechanisms around the walls of the tunnel. Now, the problem here are related to the crown and side wall stability, swelling and squeezing of rock, and problems related to groundwater. Now, two new terms are appearing here. Let me illustrate those two terms with a sketch. So let us say you have got a tunnel like this, cross section. I am drawing the cross section of the tunnel. So this is towards the top. So this point is called the crown of the tunnel, and this is the side wall that I alluded to in the previous slide. Okay, so we are likely to have some problems of rock stability of rock mass near the crown and side wall if the tunnel is to be constructed through soft or jointed rock. Now, we are going to look at the problems that are typically encountered in greater detail as we run through this lesson. Okay. The first problem, first problem that we consider here is related to a tunnel constructed through a bedrock mass which has got horizontal bedding plane. Now, here the problem, the structural nature of the problem is dictated by bending failure, by tension caused by bending. This class of problem is quite often encountered in coal mines. What happens because of this is that rock slabs across the roof cannot support its self weight, because it wants to bend and it wants to sag, and because the sagging in fact becomes so large that tension cracks develop near the bottom of the slab, and the slab could be, as a result the slab could fail. Design requirement in this case is that the tensile strength of the rock actually requires the tensile strength to exceed, not to exceed, actually I should remove this word here. So, it is not to exceed, but it is to exceed. The design requires that the tensile strength should exceed gamma L square by 2 T, where T is the thickness of the slab of the slab, rock slab at the roof of the tunnel, L is the span, is the width of the tunnel, and gamma is the total unit weight of the rock slab. Okay, so, if the tensile strength is more than the quantity gamma L square by 2 T, then the slab at the roof of the tunnel is going to remain stable in this case. Now, let us look at the failure. You should have noticed that I wiped off the word not. So, you should take a note of that. When I come back to the slideshow, it is again going to appear, but you should correct your notes accordingly. Okay. So, let us look at an animation which illustrates the type of failure in this case. So, what we have got here is a horizontally bedded rock, and we are trying to construct a tunnel, a square tunnel, and you can see as soon as the opening is made, then the slab near the roof of the tunnel is going to sag, and these are the dimensions that are indicated on the equation, on the expression there at the bottom of the slide there. So, T is the thickness, as I have already indicated, and L is the span or the width of the tunnel. So, basically what is preferred in this particular case, and that is often adopted in design, is that a square cross section of the tunnel is often preferred, is because if you have got a square cross section, then the tunnel then the slab near the tunnel crown, the roof of the tunnel is not likely to lose any thickness, and as a result the stability is going to be much more if you have got a square cross sectional tunnel. Now, compare that with another tunnel which has got this type of geometry. Here what you see is that the thickness of the rock slab, which is supposed to self support its weight, that thickness has reduced considerably over the thickness of the bedding originally. As a result, the stability of the slab near the crown is going to be compromised quite severely if this type of tunnel cross section is chosen. So, the bottom line is in this case a square cross section of the tunnel is preferable. The second type of problem that we consider here is related to inclined bedding. So, what we are going to consider here are two cases. In the first case, the bedding strike is parallel to the tunnel, and the second case we are going to consider when the bedding planes strike perpendicular to the tunnel. The first option is more susceptible to difficulties during the construction and operation of the tunnel, and the second option, in which the strike of the bedding planes are parallel to the tunnel, provides a relatively stable configuration. In order to illustrate this, I am going to show a another animation. Now, let us say we have got a tunnel constructed through a bedrock which is inclined, for which the bedding planes are inclined in that manner, and let us consider in this case the major principal stress has got the directions indicated by orange arrows. What is going to happen as soon as the opening is made, because of the direction of the major principal stress, the bedding the rock mass within bedding planes, they are going to try to squeeze into the tunnel, and this is particularly a case in case of tunnels constructed through ductile rock, and what you are going to end up with is a situation like this. So, here you can see that the portion which is to the top left of the tunnel alignment, we are again looking at the cross section of the tunnel. So, the portion which is towards the top left of the tunnel is closing into the tunnel, and this kind of a problem is called closure. So, what if we superpose the original tunnel cross section, then what we get is a situation like this. So, basically this portion here is affected by the problem of closure. This is actually, this cross section is taken from a real life problem. There recently a head race tunnel was constructed, approximately in more than 27 kilometers long head race tunnel was constructed in Himachal Pradesh as part of a project called Nathpa Jhakri. It's a project in which a 60-meter high dam was constructed, and for power generation, and the head race tunnel had this kind of head race tunnel was affected by a problem which is illustrated in that animation of the previous slide. Here the rock that was crossed, that was transected by the tunnel, was basically phyllite, and which is a ductile type of rock, and the tunnel was affected by closure as well as another type of problem which we are going to see a little bit later on. Okay. Then the third problem that we are going to get in case of tunnel constructed through rock which are laminated and the laminations are inclined. In this case, the roof slabs actually the slabs they cannot support the self weight, as was the case when we were discussing the horizontal bedding, but the problem is accentuated because of the direction of the major principal stress or the confinement or the confining stress. And if you recall, there will be a confining stress, and see if I want to illustrate this problem, let me draw a sketch here to illustrate the problem. Let us say you have got a tunnel with a cross section like this, and the tunnel is constructed through horizontally bedded bedrock, and what we are going to get in this case, if the self weight for this slab number 1 becomes too large, then it is going to sag, as we have seen in one of the previous slides. Now, if in addition to it we have got a large horizontal pressure acting on this particular slab, then you can easily notice that the problem of sagging is going to get accentuated, and this may actually become so severe that the slab near the top of the tunnel is going to fail in this process. Now, we are going to illustrate this problem with another animation, and this is the same tunnel that we are looking at when we were talking about squeezing in because of large in plane compressive stress in the previous slide, and let us see what happens in this case. So, we are looking at the same tunnel in fact as in the previous case, and here again I have marked the direction of the major principal stress, but by thick orange arrows, and it is quite obvious then that as soon as the tunnel opening is made, then the slabs are going to buckle in that manner because of the removal of confinement near the top right portion of this particular tunnel. So, that is the area where the tunnel is going to be affected by buckling problem. So, what is happening here is that because of the excavation of the tunnel, the confinement to the rock slab has been removed, and because of that the rock slab can no longer resist the buckling tendency that arises because of the presence of the pressure, the in plane compressive stress sigma, and consequently the slab buckles into the opening. This becomes an issue when you have got sigma equal to pi square E t square over 3 L square, and in this case E is the deformation modulus of the rock slab that we are considering, T is the thickness of the rock slab, and pi is the constant 3.14, and L is the unsupported span of the slab, which is shown, all these dimensions are shown on the cross section near the right of this particular slide. Now, if sigma is less than the value calculated on the right hand side, then there is no problem. If sigma exceeds this value, then the possibility of buckling has to be taken care of in the tunnel design, or supports have to be designed in order to prevent such occurrences. As I have mentioned, that this particular problem was also encountered in the headrace tunnel of Nathpa Jhakri project in Himachal Pradesh, in addition to the squeezing in problem that we discussed a few minutes back. Okay. Then we have to look at also the joint sets, how the joint sets are oriented with respect to the alignment of the tunnel. And if you recall, what joint sets are essentially cracks in the rock mass. They are many times they are closely spaced in a regular, they follow a regular pattern, and all the joints that occur in a parallel direction, we are calling them as one joint set in this case. So, two joint sets means two parallel sets of joints, relatively closely spaced parallel sets of joints oriented in an arbitrary direction with respect to the tunnel alignment. Now, let us look at the problem that are associated with this type of geologic setting. So, here again we are going to consider one tunnel. Let us say the tunnel alignment is like that, and the first joint set is oriented in that manner, and the second joint set is oriented in this manner. So, both these joint sets are striking parallel to the axis of the tunnel. So, in this case what is going to happen is that shaded area shown by orange shading near the crown of the tunnel is going to be susceptible to failure as soon as the tunnel opening is made. It is quite obvious. We will see the details of this thing in once again a little bit later. Now, let us consider another possibility in which the tunnel is oriented in a direction perpendicular to the previous tunnel. If you have got the same joint sets as before, then in this particular case for the construction of the tunnel no particular instability is going to be expected. So, to summarize what we talked in this particular problem involving double joint sets, if you have got strike of the joint sets parallel to the tunnel, then you should consider the possibility of rock fall, and if you have got a strike perpendicular to the tunnel, then you are going to have a relatively stable configuration. Let us look at the first point a little bit in a little bit greater detail. Let us say you have got a tunnel with a circular cross section as we considered in the previous slide, and you have got one joint set which is oriented in this manner, then as soon as the tunnel opening is made, then this particular wedge of rock, this particular wedge is going to fall over into the opening that is made. Now, there is another possibility that is this is not always going to be the case, because we could have a joint set that is oriented in a different manner. Let us say you have got a system like you have got a tunnel alignment like that, and the joint set is oriented in this manner. This is joint set 1 and that one is joint set 2. Then you can not always say whether this particular wedge is going to be susceptible to falling over into the tunnel opening, because the frictional strength of the surface of joint of the bottom surface of the joint and the dilatancy along the top surface of the joint, the strength because of dilatancy near the top surface of the joint. So, dilatancy here and at the bottom you are going to have a frictional strength plus dilatancy. So, these two factors is going to contribute to the stability of the wedge, and it may so happen that the wedge is going to be inherently stable and it is not going to be susceptible to fall over into the opening at all. We are going to consider this one using the problem involving multiple joint sets in this particular slide. Now, you could like what you had in case of two joint sets, you could have a tunnel alignment where there are more than two joint sets, and the problem here essentially from the standpoints of mechanics is quite comparable to what we discussed in the previous case. Here you are going to have you might have actually rock wedges falling from the roof of the tunnel, or there could be wedges falling into the tunnel by sliding from the sides of the tunnel, from the side wall of the tunnel, and those two problems are illustrated with the sketches, with the two sketches near the bottom right of this particular slide. So, here what we have is, this is the tunnel cross section, this is the tunnel opening, and this is the falling wedge. This type of wedge is called falling wedge, and if the wedge wants to slide into the tunnel from the side, then we are going to call it is generally called a sliding, actually sliding sliding wedge. Now, as a designer, your problem is to assess the stability of falling wedge and sliding wedge. So, considerations are essentially the same as we discussed in the case of two joint sets in the previous slide, involving joints striking parallel to the tunnel alignment. Now, here you have to consider the orientation, average depth and dip direction of all the different joint sets that are going to generate a possible sliding or falling wedge, and then from that, using the concept of Mohr Coulomb stability, you are going to assess whether a particular joint is going to behave in an unstable manner or it is going to behave in a stable manner, it is going to remain inherently stable. And then finally, if you find that in some cases you have got the problem of possible instability of involving falling wedge or sliding wedge, then you have to support these potentially unstable wedges. Now, let's look at this thing a little bit in greater detail. Now, let's say you have got a sliding wedge like this. We are looking at the face at the face of the tunnel wall. So, this is the top surface of the sliding wedge, and the bottom surfaces of the sliding wedge are near the are not visible actually from this angle. I am drawing an isometric here. So, these are the two bottom surfaces. So, this particular wedge is going to be, if it has to remain stable, then you have to consider the frictional resistance that is going to get mobilized on those three planes, and these are actually two planes. So, this one here is joint one, this one here is say plane 1, the bottom left plane is plane 2, and the plane at the top, let us call it plane 3. So, you are going to compute, you are going to estimate the frictional force on plane 1, then frictional force on plane 2, and the resistance, because of all these things are going to be vectorial, they are vectorial quantities, and the resistance because of dilatancy along plane 3, vector sum of those three resistances is going to be, if you add weight of the wedge to it, then what you should get is a null vector. Then the then this particular joint, this particular wedge is going to remain stable. Now, if these three quantities, when you add these three quantities, then if it exceeds the weight, then also the wedge is going to remain stable. Otherwise, this particular wedge is going to become unstable. So, here you have to consider the unit normal to the directions of the three planes P1, P2 and P3 vis-a-vis the tunnel alignment in order to compute the stability of this particular wedge. Now, if you find that the wedge is going to be unstable, then what you do? Let's illustrate this problem using a simpler configuration. Let's say let's revert back to the problem of the two joint sets striking parallel to the tunnel alignment, and let's assume that we have based on the principle of mechanics, we have assessed that the wedge which is cross hatched with a purple color there is unstable. Then what you could do is to install rock bolts in this manner in order to stabilize this particular wedge and prevent it from falling into the tunnel opening. Now, what you have to design is what these individual rock bolts are going to what load these individual rock bolts are going to carry. So, these are rock bolts, and also what is the length of each one of these rock bolts. So, that is one of the countermeasures often used in case of in order to stabilize the problem of falling or sliding wedges. Okay. Now, rockfall countermeasures we discussed we discussed very briefly in the previous slide. So, let us say we have got two joint sets. We have got a rock mass with two joint sets like that, and we are going to we are going to construct a circular tunnel of that fashion. So, obviously, in this particular case, the wedge near the crown of the tunnel is going to be susceptible to falling over into the tunnel opening, and in this case we are going to stabilize. We can stabilize actually this problem of falling wedge by installing rock bolts, as we have just now discussed. Now, another case which is the case involving a skewed orientation of the wedge. Now, here, as I have indicated, that the wedge is not always going to be unstable. You have to assess first whether the wedge is going to be stable or unstable. If you decide that the wedge is going to be unstable, then you can install rock bolts in order to stabilize this particular wedge from falling into the tunnel opening. Okay. Now, then what we are going to consider now is tunneling through folded rock mass. Now, if you recall the presentation of previous lessons, earlier lessons, then what we have discussed, that there is a strong dependence of the in situ state of stress and the regional topography, and we have indicated that the in situ stress at the bottom of a syncline actually increases several folds, maybe 3 times over the value dictated by in a horizontally bedded area, and consequently that increased state of stress is going to affect the stability of tunnel construction, as we are going to see in the next little bit. Now, what is going to happen? Let us say if you have got a tunnel being constructed through a fold of that type shown at the bottom right of this particular slide. If you recall your previous subject, your previous lessons, then this type of fold is in fact an anticline. Now, here in this particular case, what you are going to get is a much larger stress near the crowns of these folded layers. As a result, you are going to encounter difficulties of rockfall. You might actually encounter difficulties of rockfall, problems associated with rockfall, as the increased stress is released when the tunnel opening is made while crossing these folded layers. You could have similar problem in case of a syncline, a syncline fold. Now, here, as we have discussed, is the stress, vertical stress near the bottom of the fold is going to be the largest, and that is true for each one of the layers that we are seeing on this particular slide. So, these localized increases localized increased value of stresses will have to be considered when the tunnel alignment is decided and the stability issues of the tunnel wall is addressed. Okay. Now, we have looked at the problem associated with tunneling through folds. Now, let us look at the problems that you might encounter in case of construction of tunnels through faulted rock mass. So, the problems are essentially of the following types. You have to consider the activity of the fault, whether the fault has been active in recent past or not. Active faults are typically avoided during construction of tunnels if possible, and if possible is the key word there, because oftentimes what happens, you have to construct a tunnel in through faults which have been active over relatively recent geologic past, say over a few hundred years or a few thousand years. In that case, you have to account for the possible movement of the fault in the design of the tunnel itself. The second aspect related to fault activity is that the stress readjustment because of the tunnel opening itself may mobilize faults, and that is indeed a case in case of very deep underground mining operations, and it has been seen in many cases in operations of hard rock mines which can go a few kilometers, say 2 to 3 kilometers below the earth's surface, and in those situations the readjustment of stress because of the construction of tunnel opening or opening underground openings to accommodate mines facilities could be so large, they in fact have mobilized previously inactive faults which have been crisscrossing that, which crisscross that area in which the mines are constructed in a systematic manner. So, this particular fault movement actually can generate earthquakes, and those earthquakes are so near to the mine's operation that they are quite hazardous from the point of view of the safety of the tunnels. So, mine induced seismicity is a big problem of tunnel stability in case of deep underground mines operating in hard rock areas. Now, you have to also account for possible fault creep. Although the fault is not failing by a sudden movement, it could actually creep because of the removal of support or confinement in the process of construction of a tunnel opening, and this particular problem could actually lead to the difficulty of operation of ancillary facilities, such as operation of railways to cart out mined material inside the tunnel opening, and this particular problem is could be very severe in case of mines, underground mines that operate over a relatively large number of years. Then construction problem could also be possible to it is construction problems might arise in case of construction of tunnels through faulted areas, and in this case what is the problem essentially involves, because of the fact that faults are unconformal contacts in which the rock mass on either side of the fault plane, they could be of remarkably different stiffness and strength characteristics. Construction or boring of the tunnel through such areas itself could be very difficult and needs to be specially taken care of during the planning of the construction of tunnel itself. Okay. Stress concentration is another issue that should be tackled while designing a tunnel. Readjustment of stresses around tunnel opening over and above its background value, which was there which developed over because of geologic processes, may lead to yielding, rock fall and rock burst. We discussed these topics previously, so I am not going to get into the details of these things right now. Now, support requirement is an issue that needs to be tackled. It becomes apparent that in jointed rock mass you have to support the possible unstable blocks of rock around the tunnel opening. So, support requirement, assessment of support requirement is another issue tackled by engineering geologists and tunnel designers. Here I have shown a simple plot between rock mass rating and unsupported stable plan, a stable span of an underground permanent opening, and what you can see is that as the rock mass rating increases, a large length can be left unsupported without any necessity to provide any particular support in order to stabilize the rock mass. That actually illustrates one of the applications of rock mass rating that we have considered some time back. Tunnel supports, what type of tunnel supports we can have? We could install frames of steel and timber inside the tunnel opening, and that is going to support the possible unstable blocks on the roof and the side wall of the tunnel. We could install rock bolts as we have seen, or we could install liners. They include shotcrete, concrete or steel liners, which actually which are actually all in close contact along the entire surface of the tunnel wall with the surrounding rock, and because of the contact, it is going to these measures, they provide stability to the possible unstable rock mass on near the wall of the tunnel, wall and the roof of the tunnel. Groundwater issue is another issue tackled by engineering geologists while designing a tunnel. An alignment, this issue particularly arises in case of alignment that are near water bearing permeable rock layers, seepage and interception dewatering becomes a problem here, and particularly if the rocks are fractured and highly permeable. You have to also consider groundwater chemistry in this case. If you have got acid rock drainage in sulfide bearing rocks, that is a possibility, then that could actually lead to accelerated weathering of the rock near the wall of the tunnel, and consequently reduction of rock strength. Sulfates is another problem, because if you use concrete lining in case of a tunnel where groundwater is sulfate rich, then the concrete may deteriorate. There are other issues that needs to be considered. One issue is involving ventilation. Gases could escape into the tunnel. These things have to be appropriately taken care of, and then geothermal gradient has to be taken care of while designing a tunnel facility, because as we have discussed, typically temperature increases by about 30 degrees Celsius for every kilometer depth. To summarize this particular lesson, what we discussed here are major geological considerations in tunnel construction, and we looked at the measures to account for possible rock mass instability around a tunnel alignment. Now, to wrap things up, here is a question set. Try to answer these questions at your spare time, and the first question is: a circular horizontal tunnel is to cross a thinly laminated rock mass. The laminations strike parallel to the tunnel axis and dip at 45 degree to horizontal. Because of local topography, the major principal stress is parallel to the laminations. Comment on tunnel stability. Second question: how would you identify a falling and sliding rock wedge? Try to think over these solutions. I am going to give you my solutions when we meet with the next lesson. So, until now, bye for now. Thank you. Hello everyone, and welcome back. Today we are going to talk about we are going to look at a list of geologic considerations that are looked at in construction of dam, bridge and roads. But before we get on with today's topic, we are going to look at the question set of previous lesson, and here are the questions. The first question that I asked was: a circular horizontal tunnel is to cross a thinly laminated rock mass. The laminations strike parallel to tunnel axis and dip at 45 degree to horizontal. Because of local topography, the major principal stress is parallel to the laminations. You are asked to comment on tunnel stability. Now, this problem is quite similar actually to the Nathpa Jhakri tunnel, headrace tunnel that we discussed when we were talking about geologic considerations of tunnel in the previous lesson. But in that one, the tunnel had a horseshoe alignment, and here for simplicity I asked you to consider the tunnel to be circular. So, this is the tunnel cross section, and let us say the laminations are like this. Laminations are like this,